Good morning and good evening to everyone, and welcome. I'm so glad you're here today for the webinar, Accelerate Business Values with IoT Streaming Analytics. If you joined us today, you're probably curious about how IoT streaming analytics can help accelerate your business value. And over the next 60 minutes, we will walk through exactly that. I hope all of you are as excited as I am today. My name is Vishesh, and I'm going to be your host for this webinar. A couple of quick housekeeping notes before we begin. Drop your questions in the chat. We'll have a Q&A at the end. And yes, this session is being recorded. Next slide. All right. So to provide some context on who is hosting you today, we are ACL Digital, an Alton Group company. We position ourselves as a trusted AI-led digital and system engineering partner. When we look at our collective strength with our parent company, Alton, the scale is truly global. We bring over 30 years of experience to the table, serving a diverse global customer base. We are powered by a global strength of over 57,000 professionals across the world. Alton is a 4 billion plus revenue company, providing the stability and resources needed for massive digital transformation. With 35 plus design and delivery centers and 11 centers of excellence, we have the local presence to support global operations, including over 10 Fortune 100 customers. Our commitment to excellence is backed by the suite of industry standard certifications we have, including ISO 9001, AS 9100, and TISAX for automotive security, as well as CMMI Level 3 maturity. This ensures that when we are talking about IoT, we know how to do it. Now, to take us through the technical strategies, I'm pleased to introduce our speaker, Ramana Nagarajan. Ramana is a seasoned data strategist, bringing nearly 2 decades of expertise in data and analytics. He specializes in end-to-end expertise data solution, encompassing design architecture, engineering, governance, and privacy. With proven proficiency in multi-cloud delivery across Azure, AWS, and GCP, Ramana is highly focused on establishing data trust through rigorous data quality and master data management. He has successfully driven high-impact data-led outcomes across a diverse range of industries, including manufacturing, healthcare, BFSI, telecom, geophysical, and retail. On the other hand, we have Aditya Neetiselvan. She is a data analytic professional with 15 years of overall IT experience, including 5 years specializing in data analytics and advanced analytics. She specializes in designing and building scalable data platforms, modern data architectures, and end-to-end data pipelines that enable data-driven decision-making. Bringing extensive expertise in Databricks, Microsoft Azure, Apache Spark, and delivering robust ETL frameworks, real-time data processing solutions, and optimized analytical works. She has successfully driven data transformation initiatives and analytics-led outcome by turning complex data into actionable business insights. And with that, I would like to hand over the mic to Ramana. Ramana, over to you.
Thank you, Vishesh. Good morning and good evening, everyone. I'm really excited to meet you all in yet another webinar with a different title. And thanks for this. All right, let's start with a couple of stories before we get into the nuances and the technicalities of IoT and IoT data. And here is a couple of stories. Let's start with the Rolls-Royce one. Right, for decades, Rolls-Royce built some of the most sophisticated jet engines in the world and sat on a business model that was fundamentally broken. And here is the irony. They only made real money when the engines broke down and needed spare parts. If an engine ran perfectly, revenue stalled, and that's the fact. If it failed, airlines were furious. That's the other side of it. So that's business tapped by its own success. And here's the shift came from Rolls-Royce, realized something very simple and fundamental. Airlines didn't actually want to own a multi-million-dollar piece of metal. They wanted only flight hours. So Rolls-Royce stopped selling engines and something they launched called Total Gap, which is a simple data as a service model where airlines paid only for successful time in the air. They embedded thousands of IoT sensors inside every engine, streaming real-time telemetry data, namely temperature, pressure, vibration, and straight from the sky, straight to the ground. And what is the payoff? They could predict component failures days before any mechanic could see them, virtually eliminating unplanned groundings. Total Car went from niche offering to over 90% of their commercial large engine fleet, more than doubling their high margin service revenue. A cyclic manufacturer became a predictable economic powerhouse, all because they turned raw engine data into a service. And here's the second story, and which is close to our everyday life. Yes, it's a candy maker, Hershey's. Here is the hook. Growth always doesn't come from launching new products or buying competitors. Sometimes it's hiding inside your own factory walls. Yes, making Twizzlers is a volatile art. The cooking process is extremely sensitive to tiny shift in humidity, pressure, and ingredient weight. Licorice a fraction of a millimeter too thick, then it's all wasted product. If it is too thin, and it broke the packaging line, and that variance choked the production speed. So instead of building a new factory, Hershey's retrofitted its existing cooking vats with IoT sensors, feeding 60 million data points into a machine learning loop. So they dynamically adjusting cooking process in real time to compensate for microscopic atmospheric changes. And here is the result. They double throughput accuracy on that one line, which is approximately 5 million saved annually. And it unlocked manual hidden capacity without spending tens of millions on a new infrastructure. And that success became blueprint Hershey scaled across its entire global portfolio. And here is the takeaway. They are two different industries, but one identical lesson. The biggest untapped value in your business may already be streaming through your equipment right now. You just need to right way to capture it, process it, and act on it. And that's exactly will be built together for the rest of this session. With that, I would like to Aditya to explain what is IoT and IoT data. Over to you, Aditya.
Sure, Ramana. Thanks, Ramana. So in this slide, so we are going to understand what IoT really is. So what IoT data is unique. So the abbreviation is Internet of Things. So it's referred to a network of interconnected physical device. Say for example, sensors, or it could be a vehicles, or it could be a smart devices that continuously sense, communicate, and interact with the physical world. These devices generate massive amounts of data every seconds, unlike a traditional business data that is created by people through transaction. So IoT data is a machine generated data, and it will arrives continuously. So when we look at the left side of the slide, so we have highlighted few characteristics that make IoT data different. So the first thing is the high velocity time series data. So the meaning, new records are generated constantly as devices transmit readings over the time. The second thing is the volumes can be enormous because machines can generate thousands or even millions of events per second. So the third is the data is often imperfect from a streaming perspective. So events may arrive late or can be duplicated or can come out of the order, maybe due to the network delays or maybe any other connectivity issues. So the finally, so while an individual sensor reading may seem insignificant, so but the tremendous business value emerges when these readings are aggregated and analyzed at the scale. So when we look at the right side of the slide, so we could see four different important categories. So let me take you through what is the importance of those categories that falls in the IoT data. The first and foremost thing is the metadata and the context. So here this includes the information such as device identity, or it could be location, or it could be a software version, or any asset hierarchy. So that comes under the metadata and context. So the second category is the telemetry. So we know this is a continuous measurement generated by the sensors. So it could be a temperature, or it could be a pressure, or even any energy consumption. So the third category is the state and commands. So this includes the current status of devices, which is connected or not connected, and it could be any configuration settings also, and it could be any command sent to the control for or actuate the equipment. So the fourth category is the events and alarms. So these are the critical notification that indicate threshold violations, anomalies, faults, or even the operational incidents that require immediate attention. So far, we have seen the IoT devices generated massive volumes of telemetry, events, and contextual data, often in real time and extremely in high velocity. So, but generating data is the very first step. But for organization, any organization to derive value from the data, it must be reliably transmitted from devices to edge system or any cloud platform. Say, for example, whether it's a temperature sensor in a factory or even a connected vehicle in the road, just consider it's a smart meter in a network. So the success of any IoT solution depends on how efficiently and securely this data can travel throughout the ecosystem. So this raises an important questions. How do billions of connected devices communicate and exchange the information across the ecosystem? The answer is IoT communication protocols. So this will different business scenarios require different transport mechanism based on their bandwidth, or even a security, or even a power consumption. So let's explore what are the different protocols and understand which transport to choose for your specific use case. So in the next slide, so we can see what are the IoT communication protocols are there. So what is the right protocol to choose your use case? So before we step into the different protocols, so let's not stick with any single protocol. So any single protocol doesn't fit at all to any IoT scenario, because each protocol is designed to address the specific requirements such as bandwidth, power consumption, or even the security or any scalability. So let's look at some of the most commonly used protocols. So the very first and foremost thing, like everyone might have used, like MQTT. So this is a message queuing telemetry transport. This is one of the most popular protocol in IoT. So this is a very lightweight protocol, and mainly it is used in predominantly most of the projects for sensor telemetry and constrained devices, and it will operate on a limited bandwidth. So this is mostly the preferred choice for the real-time streaming data. The next protocol is a COAP. It's a constrained application protocol. So this is designed for low power devices. When I say low power devices, it is suited for the smart sensors or even the embedded devices. The third protocol is the HTTP REST. So most of you familiar with the HTTP and REST API. So though it is not defined for any IoT, so this is predominantly used for any device provisioning, configuration, or even integration with any web application. And next protocol is the LM and M2M protocol. So this is a lightweight machine to machine protocols. So it was built on top of COAP protocol, and this is focused on the device lifecycle management. It say, for example, it provides capabilities such as device registration or any firmware updates or remote management. This is a best suited one. And the next thing is the AMQP. Sorry. So AMQP is a robust enterprise messaging protocol that helps to provide the reliable message delivery and routing and queuing. It often used when IoT data to be integrated with any enterprise application. And the last protocol is OPC UA. This is used in predominantly in the industrial environment, so it has become a key standard. So it supports secure communications, rich information models, and it provides best interoperability across the automation system. So now you have got a question like when to choose the right protocol based on your business requirements. So here are the recommendation. So if the objective is streaming telemetry from sensors, so MQTT is the best fit because of the lightweight design. So if your goal is to use the remote device management, the protocols like LWM2M provide the strong lifecycle management capability. If you're planning to do any industrial automation, probably OPC UA offers a standardized and secure communication. So when integrating the IoT platform, with any enterprise system such as ERP or CRM or any data platform. So AMQP provides a reliable grade messaging. So the important point here is communication protocol are not just a technical choices. This directly influence the data latency or even the operational cost or security and ultimately the effectiveness of analytics. So if the transport layer is inefficient, even most the advanced analytics platform will struggle to generate timely insights. So we have seen how IoT devices communicate transport data across the protocol, but communication is only the part of the solution. To understand how all the components in the ecosystem fit together, I just hand over to Ramana, so who will take you through the IoT reference architecture and its layered view of modern IoT solution.
Thank you, Aditya. Thanks for the background. And now it's time to reference the layered view of the architecture. Let's zoom out the full picture. And there is a specific standard ISO IEC 3141 reference model. And there are 5 layers, data flowing. So let's start with device and perception. So this basically sensors and controllers gathering raw data. The second one is the connectivity, data moving through networks. The third one, agent gateway, where data gets processed locally for efficiency purpose, which is close to the source. And above that, we have platform layer, where data is ingested, processed, and stored. And at the top, it's application, where dashboards, alerts, and interfaces, and people actually use those data. But there are 2 main concerns across a single layer, every single layer: security and trust. That's number 1. So device identity, secure channels, access controls enforced everywhere, not bottled on at the end. And the second one is management and governance. This is basically about provisioning, monitoring, over-the-air updates, and data lifecycle policies. This layered view is the map we will use for the rest of this session. So we are about to zoom into each layer at one at a time. Let's move on to the next one. All right. So we have a couple of famous patterns. Number 1 is Lambda. The other one is Kappa. Once data is flowing, how do you architect the processing itself? 2 dominant patterns as we talk about: Lambda and Kappa. Lambda runs into two code bases side by side. Number 1 is batch path for a complete, accurate historical data. And the second one, a speed path for real-time results. So merged at the serving time. It's powerful, but maintaining dual code bases adds real complexity. And here is the other one, Kappa. This simplifies this into a single streaming path. Everything real-time and historical reprocessing runs through one single pipeline, backed by a replayable event log. So reprocessing just means replaying the log from an earlier point. So basically, both the patterns lean on the same foundation, which is a PubSub. So this PubSub event backbone that decouples producers from the consumers and the partition data by device. So the real decision point is the data retention. How long you keep that event log and how much reprocessing complexity you are willing to own. So for most greenfield IoT platforms today, Kappa simplicity is actually winning out. So with that, I would like Aditya to discuss about the design decisions. Over to you, Aditya.
Yeah, thanks, Ramana. So design decision is the part we are going to understand from the slide. So it's a very critical, important in the IoT solution. So here we are going to understand like where should the data processing actually should happen. So whether it should happen in the devices or at the edge or in the gateway or in the cloud. The answer is not always a straightforward because each option offer a different trade-offs in terms of latency, a bandwidth, cost, and scalability. So, while making a decision, so architects typically evaluate several factors. how quickly a response is required. So available network bandwidth and data privacy requirements, and what is the reliability of the connectivity, and the available compute resources on each layer. So once these factors are understood, processing workloads can be distributed across the IoT ecosystem. So let's have a quick look on the different decisions we have formulated here. So the first and foremost thing is the device edge layer. So at the device edge layer, we typically handle the operations that require extremely low latency. Examples are local control loops or filtering sensor data, event detection. These are some of the examples. Since processing happens close to where the data is generated, decisions can be made within milliseconds without depending on the network connectivity. This is especially important in industry automation, robotics, or any automated systems. The next comes the on-premises or gateway layer. So this acts as the intermediary between the devices and the clouds. So typical responsibility includes a protocol translation or buffering data during the network interruptions or stream forwarding, aggregations, and integration with IoT systems. So processing here usually supports sub-second response times while reducing the amount of data that needs to be transmitted. So the next comes the cloud platform layer. So this cloud platform layer will provide the virtual unlimited scalability and compute power. So this is where organization perform most of the analytics operations and machine learning and the historical analysis. So while the cloud layer introduces a slighter higher latency, this will enables insights across thousands or even billions of devices distributed locally. So the last thing is the latency perspective. So this is a useful way to think about this through latency requirements. So say for example, so if you are trying to control equipment that require million second level response, processing should occur at the device level. If you need the protocol translation or local aggregation with sub-second response time, then the gateway is often the right choice. And when the goal is fleet-wide analytics or predictive maintenance or business reporting, the cloud becomes a preferred processing location. So, connecting to streaming analytics. So, this is where the streaming analytics becomes more powerful because the data is filtered and acted upon at the edge, and it is enriched and routed through the gateways and then analyzed in the cloud. So, the distributed processing model allows the organization to balance the speed, cost, and the business value while ensuring the right action is taken at the right place and at the right time. So we have just discussed one of the key architectural decisions in IoT where processing should lie. So whether at the device or at the data gateway or the cloud layer. So in reality, there is no one size fits for all approach. Every organization is at the different stage of its IoT and data maturity journey. So before we deep dive into the stream analytics architecture, so let's take a quick pulse check and understand where our audience stands today. So let's move on to the poll one. So I would appreciate everyone to participate in this poll. So let's take 20 seconds. So the poll panel is live now. So there are no right or wrong answer here. So in fact, organizations across the industries can be found at each of these stages. So the goal of the today's session is to show how business can evolve from a traditional batch-oriented architecture towards a real-time or event-driven approaches. So probably we are eager to know so how your current setup. Okay. I think we got the results. So great, looks like the response are in. So let's take a look at how the audience is distributed. So looks like it's hybrid got most of the votes. So this indicates a mature transition phase. So many organizations today are balancing the reliability of batch systems while introducing the streaming capabilities for use cases that demand real-time insights. So thank you for participating. So whether your organization in batch centric or hybrid or already in streaming first, there is one challenge that everyone faces. How do we reliably ingest massive volume of IoT data without losing events or creating a bottleneck or compromising the data quality? Let's look at the key design principles that help organization ingest the IoT data at the scale. Let's have a quick look on ingesting IoT data at the scale reliability in the next slide. So, so here, one of the first challenges in any IoT platform is not analytics. It's getting the data into the platform reliably in the first place. So IoT environments generate billions of events from sensors, from machines, from vehicles. If the ingestion layer is not designed properly, so organizations can experience a data loss, duplication, and scalability issues. So this slide highlights six key capabilities that form a comprehensive IoT data ingestion strategy. So the first one is a broker-based ingestion. So message broker act as an intermediary between the producer and the consumer data. So they decouple the devices from the downstream systems and manage the connection at the scale and enable the data to be distributed to multiple consumers simultaneously. So schema, the next is the schema registry. So here the device fleet grows. A data formats can evolve over the time. So the schema registry will help enforce the compatibility between the producers and consumers. So the next comes the partition strategy. So this is very critical for the scalability. So by distributing the data across the multiple partitions, we can process large volume of events in parallel while preserving event ordering when required. So next is the delivery semantics. So this is the important consideration. So we need a mechanism such as idempotency to ensure a reliable event delivery and avoid issues caused by duplicate messages. Then next comes the edge buffering. So in many IoT deployments, connectivity may be intermittent. So this edge buffering will allow devices or gateways to temporarily store the data locally, and it will forward it once connectivity is restored. Uh, in that way, we can prevent the data loss. And the last part is the back pressure handling. So this will protect the system from overload. So when consumers cannot keep up with the incoming data rates, this platform will manage the backlog gracefully rather than allowing the pipeline to fail. So when we look at the right side of the slide, so this diagram will summarizes why this practices is matter. So without proper ingestion controls, organization definitely face a data loss as I highlighted previously and also the ordering issues. So by implementing proper broker-based ingestion and partition, whatever the points we highlighted, I think in that way they can transfer the unreliable event streams into a data that is reliable and analytics ready. So this provided trustworthy foundation for real-time analytics and business decision making. So the key takeaway is analytics is not good as the data that centers the platform. So for any reliable ingestion, we need to ensure that every downstream capability from dashboard and alerts to AI and predictive maintenance can operate only on a accurate and complete data. So reliable ingestion, I think just we I think this is a very critical part. So to make this IoT data more actionable, and we need the context and meaning around these events. So that's exactly what the next topic is all about. So I will hand over to Ramana, who will explain how adding semantic transforms a raw device signals into a meaningful business insights.
Thank you, Aditya. Right. It is very important to understand. Now, just the raw telemetry itself doesn't mean anything. What does it mean? We need to add more glossaries or more context. A number without glossary or context is just a noise. And this is where we add semantics to it. So asset equipment model give you a hierarchical representation of your physical asset. So the digital twin definitions capture device capabilities and relationships. Ontologies and vocabularies standardize the terms in units. So the temperature means, for an example, the same thing across every system. Data contracts formalize agreements on schema, semantics, and quality between the teams. And a unified namespace acts as a centralized topic space for current state. So any application can find a single source of truth for any asset it matters inside the data lake or data lake house, especially for the IoT data. And all of this enrichment happens at ingest. The early you add context, the less reconciliation work every downstream consumer has to do. So this is the difference between the streaming of numbers and the stream of insights. And with that, we need to move on to yet another important point, which is storing IoT data. This is basically now, where does this data live? IoT storage is about balancing speed against cost across 3 tiers, namely hot, warm, and the cold storage. So let's start with the hot storage. It is fast for real-time dashboards and immediate alerts. The second one is warm, basically used for query optimized, downsample rollups for regular analysis. The third one is cold, slow but cheap, and also for ML trainings, compliance, and long-term archivals. Underneath that, 4 practices matters. To start with, time series modeling. So partition by the time first, and then the device or asset. So most of you would have definitely experienced when you set up a cluster, right? So this is how we partition, and this is the industry standards. So the second one is keep high cardinality identifiers apart from low cardinality dimensions for query performance. Then the policy definition. Define retention and downsampling policy not as a manual cleanup job someone forgets to run. And the medallion refinement, raw data in the bronze, cleansed data in the silver layer, and aggregator and the business ready data in the gold layer. So, and every downstream user from an engineering debugging a fault and executive reading a KPI. So gets exactly the data speed and shape they need. And with that, we wanted to hear from you with yet another poll. So this is an interesting one. So what is the biggest challenge in collecting and contextualizing IoT data? See, here we are talking about IoT data, but in any data, it matters, right? When you collect the data and you manage it in your data lake or data warehouse, how do you add glossaries? How do you add context? And how do you manage them? Especially you want to archive and you want to split it across different, the storages. How do you feel about that? So while you're giving your thoughts about this poll, we just wanted to share one experience from one of our clients. We do have the telemetry data from the IoT data, but the problem here is the related data are scattered across different systems with a different tech stack. So actually bringing them together is really a pain. So what do you think most painful area in your organization? And that's what it is all about. We'll wait for a couple of minutes. I really encourage you to participate in this poll, please. Right, here we have the results. Okay, at least 50% of people are struggling with missing data and business context on telemetry. Yes, absolutely. Number one, we are missing the IoT data. For an example, it could be your weather perspectives or the location details or your coordinates, so on and so forth. And sometimes you might not have context around what does that particular value mean, right? Yes, we do face the same. And with that, we actually move on to the next one, which is governance maturity model.
Sure, thanks, Ramana. So here in the governance maturity model, so let's take a look at most common data quality issues that occur in the IoT streams. The first is the missing values. So this can happen in case of any dropped messages or any network interruption or device failures. So the common remediation technique includes imputation methods such as any loss known replacement. So next we have the spikes and outliers. So these may be caused by the electrical noise or any transition faults or erroneous readings. So validation rules or threshold checks are commonly used to identify such anomalies. So another challenge is a sensor drift. So where sensor measurements slowly deviate from reality over the time. This often requires cross-sensor validation, calibration, and consistency checks. So we also encounter a struck at or flatline false. So when a sensor keeps reporting the same value repeatedly while the data appears valid, it no longer reflects actual operating conditions. So then there are duplicates, which can occur because of retrace or delivery guarantees in the distributed system. So deduplication mechanisms help prevent duplicate events from impacting the analytics. So in the streaming environments, any late arriving and out of order events are extremely common. So because of varying network conditions or buffering. So proper timestamp management and event time processing becomes critical. So finally, there are unit and scale mismatches. For example, one device may report temperature in Celsius while another report in Fahrenheit. So without governance, these inconsistencies can lead to incorrect business conclusions. So on the right side, so we can see how can we balance the data quality and the cleansing. So every IoT platform must maintain the balance between identifying the data quality and applying the cleansing techniques. On one side, we have challenges such as missing values or late events or duplicates. On other sides, we have technique like validation rules or deduplication or smoothing. So the goal is not to overclean the data or lose any valuable signals, nor to allow poor quality data to contaminate the analytics. So the objective here is to strike the right balance between the downstream application and the decision makers so they can trust the data. So that we can see the governance and data quality and cleansing are the essential for building the trust in IoT data. But once we have the reliable, high quality data, the next challenge is processing the data in real time. So unlike the traditional batch system, so streaming system must continuously deal with the millions of events at different times while still producing the accurate results. So that brings our next topic around core concepts of streaming processing, a time, a windows, and state. So, in this slide, we are going to see to unlock the business value of IoT data, we need a just more data ingestion. So, in this particular thing, we need ability to continuously analyze the streams at every time. So, modern stream analytics platform are built around three fundamental concepts. So, the time, the second one is the window, and third is the state. So, when we compare the event time versus processing time, so the concept is event time represent when something actually happened in the real world. For example, when a sensor captured a temperature reading. So processing time represent when the platform receive and process the event. So in IoT environments, network delays are common. So these two times are often different. So that's why stream processing engine uses concepts like watermarks and allowed lateness to handle the late arriving events. So many of you have familiar with these terms. So this will help us to generate the accurate results. The next thing is the stateful processing guarantees. So many business use cases require platform to remember what happened previously. For example, if you want to detect whether a machine vibration has been increasing over the last 5 minutes, we need to maintain a state across the multiple events. So this is also what enables the guarantee such as exactly once processing. This will help organization avoid duplicate calculation or even any inconsistencies. So next comes is the window types. So here the common window type includes a tumbling windows or a sliding windows or a session windows. So in all these case, we can fix the interval or we can continuously move over the time or we can group the events based on the period of activity. So one classic example is, so instead of calculating the average machine temperature across all time, so we may need to calculate if every 5 minutes using the tumbling meter. So the next concept is the streaming processing engines. So all of these capabilities are implemented through a streaming processing engines such as Apache, Spark Structure Streaming, or Kafka. So these platforms provide a native support for the event time processing and state management. This helps organization to transform a continuous event streams into a actionable insights. So what is the takeaway? So, if there is one thing you want to remember from this slide, so streaming analytics is not simply processing data faster. So, it's about processing data correctly in the presence of delays, high volumes, or any continuously changing conditions. So, we have now so far we have covered how the streaming processing engine can handle data and concepts like time, windows, and state. So however, the processing data is only a part of the story. So the real business value comes when we interpret those metrics and understand what they mean and translate them into a decisions and actions. So with that, I will hand over to Ramna to cover on the analytics and interpretation.
Absolutely, dear. Absolutely, Aditya. So, how do you turn it into the decisions? This is the analytical maturity ladder, and most organizations climb it on in order. The descriptive analytics answers what happened. That's number one. Aggregations, KPIs, trends, operational dashboards. The other one is diagnostics, goes further. Why did it happen? Through the drill downs, correlation, root cause analysis, considering the asset models and operating schedules for accurate interpretation. And the other one is predictive asks, what will happen? This is basically the forecasts and the failure risks, distinguishing normal behavior from anomalies. And the prescriptive one, the top of the ladder answers, what should we do delivering the recommendations and closed loop automations? Most organizations are strong on the descriptive but weak on the prescriptive. And that's actually area of concentration. The business value compounds as you climb, but each rung depends on getting the rung below it's the first. And next one is the governance and monitoring. All right, how do you actually catch problems in real time? That's very important. Our complementary techniques, each with trade-offs. Rules and thresholds is basically static limits, fast but brittle. Statistical models, it's an adaptive detection with a low compute cost. And the other one is the machine learning. It detects complex, non-linear patterns that static rules would miss entirely. And the complex event processing, it identifies patterns across multiple correlated events in real time, not just single signal breaches. The catch with all of this part is alert fatigue. So we layer in adaptive baseline and severity scoring to cut noise and surface only what genuinely matters. So the goal isn't more alert. It is the right alerts at the right time that people actually trust and act on it. With that, Aditya will explain about the visualization.
Sure, Ramna. So far we have talked about collecting the data and how about adding the context or ensuring quality and analysis stream. But none of them is going to create a business value. So unless the insights reach the right people in a way they can easily understand and acted upon. So the first principle is the role-based design. So different stakeholders look at the same data through different lenses. So an operational manager may need fleet level performance metrics. Meanwhile, an engineer may need a diagnostic and sensor level data. So the same underlying data can serve differently for all different users. The next principle is a digital twin context. So this helps team quickly understand where an issue is occurring and what system is impacted. So next is the alert centric views. So this is rather than forcing the operator to constantly monitor dashboard as a system, we can proactively highlight any abnormal conditions. So when alert is triggered, so user can immediately access the relevant signal or trend or any operational context that need for investigation. So the next principle is a real-time dashboard. So this will provide a continuous visibility to the current state of the business such as KPI to track the KPI or any respond quickly to any emerging situation. So next is the aggregate to drill down data. An effective dashboard should also support the journey from summary to detail. So user often start with the fleet level health metrics, then drill down to the specific site, and then assert and then subsystem, and eventually individual sensor readings. So the next thing is the show data refreshness. So user need confidence that they are making a decisions based on the current information. So showing the update items, latency indicators, data quality will help us building the trust in the platforms. So analytics will tell what is happening. Visualization will help people to understand and act on it. So far, we have focused on understanding what's happening now throughout the real-time dashboard. So instead of reacting to the failure after they occur, can we identify warning signal early enough to prevent them? That's where predictive analytics comes in. So with that, hand over to Ramana.
Thanks, Aditya. This is where everything we have built payoffs. Predicting failure before it happens, that's really important. The pipeline starts with historical data, enable, run to failure, and maintenance records joined with telemetry. Feature engineering extracts lowering statistics, deltas, and spectral of FFT features from the vibration and the current signals. Model training uses a gradient boosting survival analysis or LSTM sequence models, validated with honest time-based split, never random splits. So, which would leak the future into training. Deployment run, batch scoring, or online inference, including on edge for low latency, and the output remaining the useful life estimates feeds directly into maintenance, planning, and spares ordering. So two things keep this trustworthy long term. ISO standards, ISO 13374 for condition monitoring, and ISO 10816 or 20816 for vibration severity. So ground your models in acceptance engineering practice and MLOps integrity, versioning data, feature, and models, monitoring for input drift, and retraining on triggers rather than calendar shadow deploying before you ever promote a new model into production. So this is exactly Rolls-Royce story, operationalized as a repeatable pipeline. And with that, we would wanted to hear one more time in this webinar with yet another poll. So this is to understand what is your prediction in terms of the future. I mean, in next 12 months. Let's wait for one more minute, and I would request everyone to participate for this. Right? I guess it's time for the results. Great. It's almost mixed of everything. That's interesting. Yeah. Let's see how it goes in the future. All right. With that, we also wanted to showcase one more demo, which we used it for one of our clients. In fact, over to you, Aditya.
Yeah, Ramna. So let's switch over.
Yes.
Yeah. So let's switch over to the live demo and see how these capabilities, whatever we have discussed in the previous slides, and come together in a real world solution. So let me quickly demonstrate how machine learning can help detect anomalies in IoT sensor data. So in this example, we are analyzing the data from an air handling unit or critical HVAC component. The goal is to identify abnormal operating behavior before it impacts efficiency or lead to equipment issues. This demo uses a real world HVAC dataset collected from an energy facility in Turin, Italy. So the data spans approximately 8 months with sensor reading captured every 15 minutes. So this dataset includes a temperature, humidity, and operational parameters that help us understand how the equipment normally behaves. So we are going to talk about anomaly. What is an anomaly? So it's not a failure, it is simply a behavior that differs from the normal operating pattern. For example, the temperature reading may still be within the acceptable range, but when we compare the relationship with other sensor, it may be unusual. So machine learning will help identify these subtle deviations much earlier than traditional rule-based monitoring. So in the dashboard, so in the upcoming dashboard, you could see we have used two anomaly detection approaches. So the one is the rolling Z score, the next is the isolation forest. So the rolling Z score identifies a deviation from the recent behavior. So while isolation forest uses machine learning to identify the observation that appears differently from majority of the data. So notice the sensitivity slider. So by adjusting the sensitivity, we can control how aggressively anomalies are detected. Higher sensitivity flags more events, while the lower sensitivity signal focus only on the most significant anomalies. So, what is the business value this is going to give? So, finally, this business dashboard translate any technical inputs to a actionable insights. So, we can see the percentage of healthy operations of any anomalous periods and the potential impact on energy consumption. So, the key takeaway is that machine learning enables teams to detect abnormal patterns early, prioritize maintenance activity, and reduce the downtime and improve the operational efficiency. While this example uses HVAC data, so the same approach can be applied to any manufacturing requirements, equipments, or any industrial machines or any IoT based assets. So we have seen how IoT sensor data combined with machine learning and will help us in identifying the anomalies and improve the overall efficiency and support proactive maintenance. This concludes the demonstration on anomaly detection using IoT data and machine learning. So with that, I would like to open the floor for questions and discussion.
Right.
We're
Let's
having
share
a
the
question here. The question is, we're a batch first organization. All our sensor data lands in a data lake nightly. What's the pragmatic first step towards streaming without a big bang rewrite?
Sure, Vishesh.
Right? Yeah.
Yeah. So I think they are using the batch-based processing. I think they want to transform to the streaming. So the first step is to introduce a small streaming layer for just try to get some identify some business critical use case. Could be anything based on your organization thing. So just try to understand what that critical use case is going to give benefits from the real-time insights. So next thing, we need to stream only the new incoming sensor data. So rather than we need to re-engineering the whole historical workload, that is going to take more cost. So just based on your critical use case, just try to stream only the new incoming sensor data, and you can use any Databricks structured streaming to process and enrich the events. And once that done, you can store the outputs in any lakehouse or data lake, and you can maintain a single source of truth. So in that way, you can gradually migrate additional workloads to streaming. So in that way, you can prove the business value. So in it is not advisable or recommended to move your entire platform or the skeleton to streaming in one stage. Let's go phase by phase panel. As I said, start with critical and with the new incoming data, and then go with low priority ones.
All right. Thank you, Aditya. Ramana, can you kindly share the screen, please, of the PPT? All right. With that, we have another question. Says, how do you handle devices whose clocks are wrong? Event time processing assumes the timestamp is trustworthy.
Sure, Vishesh. I think this is a predominant expectation like happen in any of the IoT streaming. Like, so we need to basically, not sure who asked this question. So basically, we need to validate the device timestamps against any acceptable clock skew threshold. So you can use any ingestion time as a fallback when the device timestamps are missing or clearly incorrect. You can use some watermarking or late arrival handling to accommodate any delayed events. And you can also flag any suspicious timestamp for correction for your downstream data quality checks. So the goal is not to assume the timestamp always trustworthy. You have to build the resilience to the streaming architecture so that a data remains reliable even when the device clocks or not. So time is treating time as a data quality attribute and capture multiple times.
Vishesh, I guess there is a technical glitch. Probably we can move on.
All right. Um, yeah, there are no more questions in our hand as of right now. So with that, it brings us to the end of today's session. And of course, yeah, what an insightful session it has been. I'd like to take a moment to thank you all, especially our speakers for sharing your valuable insights on accelerating business values with IoT streaming analytics. The depth of knowledge and the real world perspective you brought today was absolutely appreciated. And I'm sure everyone on this call has definitely walked away with something great today. Whether they are learned about fresh way to think about streaming data or practical strategies for digitizing operations or ideas to accelerate transformation within their own organizations. And to all our attendees, thank you so much for joining us today and for being an engaged audience throughout the session. We hope this discussion gave you meaningful insights that you can carry back and apply on your own business and challenges that you're facing. If we did not get your specific question or you'd like to dive deeper into how ACL Digital can help, please reach out to us. Visit us at acldigital.com to explore our centers of excellence and keep an eye on your inbox. We'll be sending out the full recording of today's session within the next 24 to 48 hours. That way, if you missed any part of the discussion or want to revisit something, you'll have it handy. So on behalf of ACL Digital and Alton Group, Vishesh, thank you again for being here. We look forward to see you again in our next webinar. Have a wonderful day ahead or a great evening ahead. Thank you all.
Thanks all.
Thank you all.